Welcome back, everyone, to the deep dive. Today, we're going to be looking at T-symmetry.
Ooh, that's a fun one.
Yeah, it's a pretty wild idea. Basically, it's this notion that the laws of physics should work, whether time is running forward or backward.
Yeah, you just take t to minus t and everything should look the same.
Exactly, and in our everyday experience, we know that doesn't really seem to be the case.
Right, like if you spill a glass of milk, it doesn't unspill itself.
Yeah, my coffee doesn't jump back into the mug in the morning. I wish it did.
Yeah, you can't unscramble an egg.
Mm-hmm.
So it feels like time has a very particular direction and that it's asymmetric.
Yeah, and the culprit there is entropy, right?
Yeah, that's the second law of thermodynamics. Entropy always has to increase.
Okay, so finally, the article ends with this really cool and recent discovery from the University of Toronto in 2024, where they observed what they call negative time behavior of photons under certain quantum conditions. Can you tell us about that?
Yeah, this is a super exciting result. So in their experiments, they had these photons interacting with clouds of atoms that were prepared in a very specific way. And what they found is that the photons appeared to exit the atomic medium before they had fully entered it.
Wait, so they were traveling backwards in time?
Well, it's not quite that simple,
Mm-hmm.
but it does seem like they were getting a head start, like they were somehow anticipating their interaction with the atoms. And this is a phenomenon called negative group delay, and it's been predicted theoretically for a long time. But this is the first time it was observed experimentally.
Wow, that's amazing. How did they actually measure this?
So they use this really clever technique involving the cross-Kerr effect, which basically allows you to measure the excitation state of an atom by looking at the phase shift of a probe laser beam. And what they found is that the atoms were getting excited before the photons should have arrived.
That's so wild. So it's like the photons were traveling backwards in time with respect to their interaction with the atoms?
Yeah, it's a really counterintuitive result. And the researchers emphasize that this is a purely quantum mechanical effect. It wouldn't happen in classical physics.
So this is another example of how quantum mechanics can lead to really strange and unexpected behavior.
Definitely. And this discovery could have some really interesting implications for quantum computing and photonics. Like maybe we can use this negative group delay effect to speed up quantum computations or to manipulate light at the single photon level.
Yeah, that's super cool. So the material we've been looking at for this deep dive sort of outlines three, main categories of this, like why time seems to have this arrow. So first is, some of the fundamental forces themselves might just have time asymmetry baked in.
Right, the weak force.
Yeah, the weak force is a good example.
Yeah.
Second is, the initial state of the universe. Like maybe that's responsible for this arrow of time that we see.
Right, and that's kind of tied into this idea of entropy, like how much entropy was there at the beginning of the universe.
Right, and then third, and this one is super weird, is that even the act of measuring something, like a gentle measurement in the quantum world could theoretically introduce a time asymmetry.
So like just the fact that we look at things and try to find out what they're doing might actually be giving time a direction.
Yeah, which is really trippy. So the article we're looking at today really digs deep into T-symmetry. And so I guess our goal in this deep dive is to really explore, why time seems to have this one-way street. And think about those situations where maybe that's not the case.
Yeah, like are there loopholes? Are there ways to get around this arrow of time?
So I think a good place to start would be just the world we live in, the microscopic world. And the article gives a really cool analogy with a teeter-totter. So imagine a teeter-totter that's balanced on a point. And, in a perfect world with no friction, you give it a push, it'll just rock back and forth forever. And that's kind of, it's a good picture of time reversal symmetry or time reversal invariance.
Right, because if you were to play that motion backwards, it would look exactly the same.
Exactly, yeah. So.
But then the real mind-blowing part is that obviously that's not what happens in real life. In real life, that teeter-totter is going to come to a rest. It's going to fall off that balance point and land on the ground. And that's not because Newton's laws of physics stopped working. It's because entropy took over. Because there are way more configurations of that teeter-totter where it's lying on the ground than where it's precariously balanced on that one point. So basically, the universe is always going to move towards states where there is less information about what's going on, like on a microscopic level where everything is. And so that probabilistic element that there are more ways for things to be disordered than ordered is kind of what gives us the arrow of time.
Yeah, it's like the universe is lazy and just wants to be in the the easiest, most common state.
The laziest state, the state that requires the least amount of information to describe it.
Yeah, exactly. And so we see that, in a lot of everyday examples, right? Like friction slowing down a rolling ball, or, the way thick fluids resist motion. These are all examples of the second law at work.
Right? All that useful energy that you put into getting that ball rolling or stirring that fluid eventually dissipates and turns into heat. And that heat is like the most disordered form of energy there is.
Yeah, you can't really use heat to do work in the same way. It's just sort of spread out everywhere.
Right. It just increases the randomness, the overall disorder of the molecules in that system. And this whole idea of entropy decreasing actually led to a really famous thought experiment called Maxwell's demon. So imagine you have this tiny little demon, and he's guarding a doorway between two chambers of gas.
Oh, I love Maxwell's demon. This is a good one.
Yeah, and he's got like this little tiny door, and he can open and close it really, really fast. And so this demon is really smart, and he's able to sort the molecules in the gas. So he only lets fast molecules into one chamber and slow molecules into the other chamber. And so what this does is it creates a temperature difference between the two chambers.
Right, yeah, because temperature is just like the average speed of the molecules.
Right, exactly.
Yeah.
And so by creating this temperature difference, it seems like he's actually decreasing entropy locally. Like he's making one side hotter and one side colder. And so it almost seems like a loophole, like maybe you could reverse the flow of time if you had this really clever demon.
Yeah, like a little Maxwell's demon refrigerator.
Right. But here's the thing. When you actually take into account the demon himself, like how is he making these decisions? How is he getting the energy to open and close this little door? You realize that the total entropy of the whole system, the demon plus the gas, actually goes up.
Right. He's got to use energy to measure the speed of the molecules, and then he's got to compute which ones to let through.
Right. And all of that computing, all of that measuring takes energy, and that energy eventually gets dissipated as heat. So the universe is really good at balancing its books. There's no such thing as a free lunch when it comes to entropy.
Yeah, so there's no escaping the second law.
Right. And actually, this ties into a lot of really cool modern ideas about computing. There's this idea of reversible computing, where you try to design computers that don't erase information, which would create entropy. And then there's quantum computing, where the rules of the game are a little bit different. But even in quantum computing, you still have limits imposed by entropy, like the very act of processing information has an entropic cost.
Yeah, that's super fascinating. And the article mentions this idea called the Boltzmann-Shannon identification. And it basically links the, logarithm of the volume of phase space to like negative Shannon information, and then that's also linked to entropy. Can you maybe unpack that a little bit? It sounds pretty complex.
Yeah, no, it's a pretty deep idea, but it's actually pretty intuitive when you think about it. So imagine you have a glass of water.
Right.
Okay, you want to describe the exact state of that glass of water, like where every single molecule is how fast it's moving. And so to do that, you would need like an insane amount of information, right? You need to know the position and momentum of every single molecule in that glass.
Like a crazy amount of information.
Right. And so phase space is this like mathematical space that contains all the possible states of that glass of water, every possible arrangement of those molecules and their velocities. And so low entropy means that we're in a very tiny corner of that phase space. Like we have a very specific ordered arrangement of those molecules.
Like if it was ice.
Exactly like an ice cube. All the molecules are locked in a very specific crystal structure. We know exactly where everything is. But then as time goes on and the ice melts, the number of possible arrangements of those molecules just explodes. Like there are way more ways for those molecules to be arranged in liquid water than in solid ice.
Yeah, they're just like bouncing around randomly.
Right. And so that means that the volume of phase space that corresponds to liquid water is way bigger than the volume that corresponds to ice. And that increase in volume, that means there's more uncertainty about the exact microscopic state of that water. And that's what we call high entropy. It's like we've lost information about the initial ordered arrangement of the molecules.
Right. It's like you said before, the universe just wants to be in like the easiest, lowest information state.
Right. And so by going from ice to water, we've actually increased the entropy of the universe because we've lost information about the specific arrangement of those molecules.
So it's not just about things getting messy. It's about the universe moving towards those states where we just know less about the details of the past.
Exactly.
Okay, so speaking of the past, let's talk about the Big Bang. How does the origin of the universe factor into this whole discussion about time asymmetry?
Okay, so this is where things get really interesting. The prevailing idea is that the fact that entropy always increases might not actually be like a fundamental law of physics, but rather it's just a consequence of the initial state of our universe. Like maybe our universe just started out in a really, really low entropy state.
So it's not that entropy has to increase, it's just that it started out so low that it has nowhere to go but up.
Exactly. Think about it. If the universe started out in a state of maximum entropy, like in a so-called heat death, then entropy couldn't increase anymore because it would already be as high as it could possibly be. And if entropy isn't changing, then there's no arrow of time.
Wow, that's mind-blowing. So our experience of time moving forward could just be because the universe started out in this ridiculously organized state.
Right. And this is actually supported by observations of the cosmic microwave background radiation, which is like the afterglow of the Big Bang. And what we see is that it's incredibly uniform, like it's the same temperature in every direction. And that tells us that the early universe was incredibly smooth and homogeneous, which means it had very low entropy.
So it's almost like the universe started out as this like perfectly arranged cosmic egg.
Yeah.
And then it's been slowly unscrambling itself ever since.
That's a great analogy. And it leads to a really profound question. Why did the universe start out in such a special low entropy state? Like what were the initial conditions that gave rise to the arrow of time that we experience?
Yeah, that's a huge question. Maybe one for another deep dive.
Definitely.
Okay, so let's move on to something even more mind-bending, black holes. So the article says that while classical gravity itself seems to be time-symmetric in its equations, black hole solutions might not be. What's going on there?
Okay, so black holes are just fascinating objects. And one of the things that makes them so weird is the nature of their event horizon. So anything matter, light information can fall into a black hole, but classically nothing can escape, except for this really subtle quantum mechanical effect called Hawking radiation. But for the most part, things just go in and they never come out.
Yeah, it's a one-way trip.
Right, and that's because the fabric of space-time is so warped around a black hole that even light cones get tilted inwards. And light cones are what define the possible paths that things can take in space-time. So once you cross the event horizon of a black hole, all paths lead to the singularity at the center.
Like there's no going back.
Right, and in that kind of extreme environment, it becomes really difficult to even define what time reversal would mean.
Yeah, I guess like if everything is just inevitably moving towards the singularity, then what does it even mean for time to run backwards?
Right, and then you have this hypothetical object called a white hole, which is like the time reversal of a black hole.
Oh, yeah, like the opposite of a black hole.
Right, so a white hole you can't enter from the outside. And instead of having a beginning like a Big Bang, a white hole has an endpoint. And its light cones point outwards. So classically, if you were to reverse the movie of something falling into a black hole, you would expect it to emerge from a white hole.
Okay, so it's like a black hole running in reverse, but
right.
the article says that it's more complicated than that.
Yeah, it is. So our modern understanding of black holes is starting to link their irreversibility to the second law of thermodynamics. So we now think of black holes as thermodynamic objects. They have their own entropy. And that entropy is proportional to the area of the event horizon.
Wait, so the bigger the black hole, the more entropy it has.
Exactly. And so when something falls into a black hole, the area of the event horizon increases, which means the entropy of the black hole also increases. And so this increase in entropy might actually be what's driving the irreversibility of black holes. It's like the black hole is a giant entropy sink. Things fall in, entropy goes up, and there's no way to reverse that process without violating the second law of thermodynamics.
So it's not necessarily that gravity itself is time asymmetric. It's more like the irreversibility is an emergent property of this entropy increase.
Right. And there's this really cool idea called the gauge-gravity duality conjecture, which suggests that at the most fundamental level inside a black hole, the underlying processes might actually be reversible. But the macroscopic irreversibility that we observe is just a collective thermal behavior.
Yeah.
Just like any other large system that obeys the second law of thermodynamics.
Whoa, okay, that's pretty deep. So like even though it seems like black holes are the ultimate example of irreversibility, there might be some underlying reversibility at play at the quantum level?
It's possible. It's one of the biggest mysteries in physics right now.
Yeah, well maybe we'll solve it on another deep dive someday. But for now, let's zoom back out and go down to the microscopic realm. So the article talks about this concept of microscopic reversibility and its kinetic consequences, like detailed balance and on-Sager reciprocal relations. What does it mean for the fundamental equations governing individual particles to be T-symmetric?
So at the most basic level, the equations that describe the motion of individual particles in classical mechanics, like those billiard balls we were talking about earlier, they are invariant under time reversal. So if you could reverse the velocities of all the particles in a system at some instant in time, they would retrace their paths backwards and everything would look exactly the same. The underlying physics doesn't care if time is running forward or backward.
Okay, but then why does the macroscopic world look so irreversible if the microscopic laws are reversible?
That's because the irreversibility we see in the macroscopic world comes from the statistical behavior of huge numbers of particles. Like we were talking about with phase space, there are just way more ways for things to be disordered than ordered. And so even though the individual interactions between particles are reversible, the overall evolution of a system with trillions upon trillions of particles is going to be overwhelmingly likely to move towards states of higher entropy.
So it's like a law of large numbers thing. Like the more particles you have, the more likely it is that entropy will increase.
Exactly. Microscopic reversibility is a property of the individual interactions between particles, but macroscopic irreversibility is a property of the collective behavior of a huge number of particles.
Okay, that makes sense. And then the article goes on to list a bunch of classical physics variables, and it categorizes them as either even or odd under time reversal. Can you give us some examples of that? Like, what does it mean for a variable to be even or odd?
Sure. So a variable is even under time reversal if its value stays the same when you reverse time. So like position, acceleration, force, energy, those are all even variables because they don't depend on the direction of time.
So, like, if I throw a ball up in the air, its position and its energy are going to be the same whether time is running forward or backward.
Right. On the other hand, a variable is odd under time reversal if its sign flips when you reverse time. So like velocity, momentum, magnetic field, those are all odd variables.
Okay, so if the ball is moving upwards, its velocity is positive. But if we reverse time, it's moving downwards, so its velocity is negative.
Exactly. And the magnetic field is a really interesting case because it might seem like it breaks time reversal symmetry.
Yeah.
Because the force on a charged particle moving in a magnetic field, the Lorentz force depends on the velocity of the particle.
Right, so it seems like the direction of time matters there.
Yeah, it does seem that way. But the thing is that the magnetic field itself also reverses under time reversal because magnetic fields are generated by electric currents, which are just flautas of charged particles. So when you reverse time, the direction of the current flips, and so the direction of the magnetic field also flips.
Oh, so it all works out in the end.
Exactly. So classical charged particle motion in electromagnetic fields is still fundamentally T-symmetric.
But the article does mention that it's sometimes useful to consider a local T asymmetry, like with a fixed external magnetic field.
Right, and that can be helpful for analyzing specific phenomena.
Yeah.
Like in Faraday isolators, which are devices that let light pass through in one direction but not the other.
That is cool.
Yeah, it's a really neat application of this idea of local time reversal asymmetry. But ultimately, the underlying laws of electromagnetism are still T-symmetric.
Okay, so now let's talk about quantum mechanics. How does this whole time reversal thing work in the quantum world?
All right, so this is where things get a little bit trippy. So in quantum mechanics, symmetry operations are represented by operators. And these operators can be either unitary or anti-unitary.
Okay. I'm not super familiar with those terms. Can you explain the difference?
Yeah, so a unitary operator basically preserves the inner product between two quantum states, which means it preserves probabilities. So if you apply a unitary operator to a quantum system, the probabilities of different outcomes don't change. And parity, which is the operation that mirrors spatial coordinates, is a unitary operator.
Okay, so parity is like looking at the universe in a mirror.
Right, exactly. But time reversal, in order to preserve the fundamental relationship between position and momentum in quantum mechanics, it has to be an anti-unitary operator.
Okay, and what does that mean?
So an anti-unitary operator is kind of like a unitary operator, but with an extra step. It also involves complex conjugation, which basically means you flip the sign of the imaginary unit I in quantum mechanical equations. And one of the reasons why time reversal has to be anti-unitary is because of energy. If time reversal were unitary, it would flip the sign of the energy of a quantum state.
But energy should always be positive.
Right. And so by being anti-unitary, time reversal not only reverses time, but it also flips the sign of I. And this combined action ensures that the energy stays positive.
So it's a much more subtle operation than just reversing the flow of time.
Right. It has to take into account this complex structure of quantum mechanics.
And the article mentions the specific form of the time reversal operator for a particle with spin.
Yeah. So for a particle with spin j, the time reversal operator can be written as t equals e to the minus I pi j over h bar times k, where j is the y component of the spin operator, and k is the complex conjugation operator. And this ensures that the spin vector of the particle reverses direction under time reversal.
Okay, so it flips the spin as well as time.
Exactly. And this has some really interesting consequences for electric dipole moments, or EDMs.
Okay, remind me what an EDM is again.
Yeah, so an electric dipole moment is basically a measure of the separation of positive and negative charge in a system, like a measure of how asymmetric the charge distribution is. And it's a vector quantity, which means it has both magnitude and direction. And so in a quantum state that respects certain symmetries, the expectation value of this EDM vector has to be aligned with any other intrinsic vector property of the system, like its spin.
Okay.
And so under a parity transformation, which is spatial inversion, the EDM flips its direction because you're basically flipping the system around. But scalar quantities like energy should remain unchanged. So if a system has a non-zero EDM, that means its energy would also flip under parity. And that's a contradiction. So a non-zero EDM in a system that's invariant under parity would violate parity symmetry.
Okay, I think I'm full.
And similarly, under time reversal, the spin of a particle reverses its direction. So if a state with a non-zero EDM were also invariant under time reversal, the EDM would have to flip sign while the state itself remains the same. And again, that's a contradiction. So a non-zero EDM in a state that's invariant under time reversal would violate T symmetry.
So that's why the article says that a non-zero EDM violates both P and T symmetry.
Exactly. It would mean that the system is not symmetric under either parity or time reversal.
But then the article also mentions this exception with molecules like water that can have an EDM without actually violating T symmetry.
Right. That's because they have what's called degenerate ground states under parity. So if a quantum system has multiple lowest energy states that transform into each other under parity, then it can have a non-zero EDM without necessarily violating T symmetry.
Okay, so it's a special case.
Yeah, it's a really cool exception.
And this whole idea of EDMs is really important for experimental searches for new physics, right?
Yeah, absolutely. Because if we were to observe a non-zero EDM in a fundamental particle like a neutron or an electron, that would be a huge discovery. Because it would mean that there are new sources of T violation beyond what we currently know in the standard model of particle physics.
So it's like a window into new physics.
Exactly. And there are a ton of experiments going on right now trying to measure the EDMs of neutrons and electrons with incredible precision. But so far, they haven't found anything, which actually puts some pretty strong constraints on theories that try to explain physics beyond the standard model.
So it's like these null results are actually telling us something about the universe.
Yeah, they're telling us that the universe is more symmetric than some theories would predict.
That's amazing. So even not finding something can be a big deal in physics.
Definitely.
Okay, so the article then talks about Kramer's theorem, which has to do with this anti-unitary nature of the time reversal operator. What's that all about?
Okay, so Kramer's theorem applies to quantum systems where the Hamiltonian, which is like the energy operator of the system, is invariant under time reversal. So if you apply the time reversal operator twice to a quantum state and you get back the original state but with a minus sign, then that state has to be orthogonal to its time reversed counterpart.
So if t squared equals -1?
Exactly. And if two states are orthogonal, that means they can't be the same state. So this forces a twofold degeneracy in the energy levels of the system.
Meaning there have to be two states with the same energy.
Right. And this theorem is really important for systems with an odd number of fermions, which are particles with half-integer spin. And it kind of foreshadows the deeper connection between spin and statistics and quantum field theory.
So it's a pretty deep result.
Yeah, it's one of the foundational theorems in quantum mechanics.
Okay, and then for quantum states where applying the time reversal operator twice gives you back the original state with a plus sign, there's this concept of T parity.
Right, so if t squared equals +1, then you can define this thing called T parity, which is basically a multiplicative quantum number. It tells you how the state transforms under time reversal. And it's another way to classify quantum states based on their symmetry properties.
Okay, cool. So now let's shift gears and talk about the standard model of particle physics, which is our current best theory of fundamental particles and forces. So the article says that the standard model has CPT symmetry. What does that mean?
So CPT symmetry means that the laws of physics are invariant under the combined operations of charge conjugation, parity, and time reversal. So you flip the charges of all particles, you mirror the spatial coordinates, and you reverse time, and the physics should stay the same.
So it's like the ultimate symmetry.
Right. And it's actually considered to be a fundamental principle in relativistic quantum field theories. But here's the thing. While CPT symmetry is a symmetry of the standard model, time reversal symmetry on its own is not. And this is what we call CP violation.
So the standard model violates time reversal symmetry.
It does in a very subtle way. It actually violates the combined operation of charge conjugation and parity, which means that if you flip the charges of all the particles and mirror the spatial coordinates, the physics actually changes.
Okay, so it's not symmetric under CP.
Right, and because of this deep connection between charge conjugation parity and time reversal, CP violation implies P violation.
So time reversal symmetry is broken in the standard model, but the article mentions that there are two sources of CP violation that we know of.
Right, so one source is the mixing of quark flavors in weak decays, which is a process that we've actually observed experimentally. And the other source is a potential direct CP violation in the strong interactions, which is something that we haven't observed yet, but it's allowed by the theory, and there are a lot of experiments looking for it.
Okay, so we know for sure that time reversal symmetry is violated in the weak force.
No.
And it might also be violated in the strong force, but we're not sure yet.
Right, and this is a really big deal because it means that the universe has a fundamental asymmetry between matter and antimatter.
Yeah, I remember reading about that. Like, why is there more matter than antimatter in the universe?
Right, that's one of the biggest mysteries in cosmology. And CP violation is one of the key ingredients that might explain it.
So this is a really deep connection between particle physics and the evolution of the universe.
Definitely.
Okay, so it's really important to emphasize that this T violation in the standard model is distinct from the time asymmetry we experience due to the second law of thermodynamics.
Right, those are two completely different things. The T violation in the standard model is a fundamental asymmetry in the laws of physics themselves, whereas the second law of thermodynamics is more like an emergent property of the statistical behavior of large numbers of particles.
Right, so it's not that time itself is running backwards in the standard model. It's more like the laws of physics themselves have a slight preference for one direction of time over the other. Okay, so the article then brings up this super weird idea about the time reversal of non-invasive measurements in quantum mechanics. It says that even measurements that don't strongly disturb this system are theoretically predicted to violate time symmetry, even in equilibrium, and that this is different from classical physics, where non-invasive measurements don't violate time symmetry.
Yeah, this is one of the most mind-bending predictions of quantum mechanics. The idea is that even if you do a measurement that ideally shouldn't affect the state of a quantum system very much.
So it seems like our journey today has taken us from the macroscopic world of teeter-totters all the way down to the quantum world of photons traveling backwards in time. And it's clear that our understanding of time and its underlying symmetries is far more complex and nuanced than we might have initially thought.
Right, like our everyday experience tells us that time moves forward in a straight line. But when you start digging into the fundamental laws of physics, things get a lot weirder.
Yeah, and I think the big takeaway here is that the arrow of time might not be as absolute as we think it is. Like, there might be loopholes or exceptions where time can behave in unexpected ways.
Especially at the quantum level.
Exactly, and that's what makes physics so fascinating. There's always more to discover. So to wrap things up, I'd like to leave our listeners with a final thought. Given these recent discoveries about negative droop delay in quantum systems, could it be that our intuitive notions of cause and effect are more flexible than we think? Like, what other seemingly fixed aspects of our reality might be challenged by future discoveries in quantum mechanics? It really makes you wonder about the nature of time and how it relates to our perception of the universe.
Yeah, it's a question worth pondering. And I think it's a good reminder that we should always be open to new ideas and new ways of thinking about the world.
So thanks for joining us on The Deep Dive, and we'll see you next time.
See you next time.